Hi everyone and welcome. Today we are diving into one of the most exciting and challenging topics in AI, how to build a large language model or LLMs from scratch. These models like GPT, Llama, and Falcon are transforming industries from customer service to creative writing and even scientific research. In this video, I'll guide you through a step-by-step through the process of building an LLM, touching on the complexities, costs, and decisions involved. Here's what we'll cover in this video. First, we'll explore data curation, the backbone of any successful LLM. Next, we'll dive into model architecture, where we'll break down how transformers power modern LLMs. Then, at training and scale, we'll uncover the techniques that make training such massive models possible. And finally, we'll wrap up with evaluation, because a trained model is just the beginning. Along the way, we'll touch on practical insights, challenges, and considerations you may encounter. But first, let's break down the costs of building a large language model. As you can see, the computational demands of training an LLM are enormous. For example, training the Llama 2 model with 7 billion parameters required approximately 180,000 GPU hours. Scaling that up, the 70 billion parameter version took 10 times as much to compute, around 1.8 million GPU hours. To put this in context, training a 10 billion parameter model would require 100,000 GPU hours, costing approximately 1.2 crore rupees if you rent GPUs. For a 100 billion parameter model, you are looking at 1 million GPU hours, costing about 12 crore rupees just for compute time. Now, when it comes to renting GPUs, cloud providers like AWS or Azure offer NVIDIA A100 GPUs at rates ranging from 80 rupees to 160 rupees per GPU hour. Renting is a practical choice if you're doing one-off training or testing smaller scale models. However, for large operations, buying your hardware might be more cost-effective in the long run. Each NVIDIA A100 GPU costs roughly 8 lakh rupees. To form a cluster of 1000 GPUs, you'd need an investment of around 80 crore rupees just for the hardware. And this doesn't include operational costs like electricity, cooling, and data center management. So the takeaway here is essentially that building an LLM is not just a technical challenge, but a significant financial commitment. For many, fine-tuning an existing model can be a more practical and economical alternative. Diversity in your dataset is critical. Imagine training a model only on news articles. It would struggle with conversational tasks or code generation. This slide shows how different models prioritize data types. For example, GPT-3 relies heavily on web pages, while PaLM includes significant conversational data. A balanced dataset ensures versatility, and for instance, if you're building a model for healthcare, including scientific articles, patient records, and conversational data would create a robust, specialized tool. Data preparation involves 4 key steps. Quality filtering. This means removing low-quality, toxic, or nonsensical text. For example, web scrape data often includes duplicates or spammy content that adds noise to training. Deduplication. Repeated text can bias your model. For instance, if the same web page appears in both training and testing datasets, your model might score unrealistically high in evaluation. Privacy reduction. Imagine scraping a forum and accidentally including sensitive user data. That's a recipe for legal trouble. you must redact anything confidential. And lastly, tokenization. This step converts text into numbers. Algorithms like byte-pair encoding create subword vocabularies, enabling models to process text efficiently. With data ready, it's time to design the model. At the heart of modern LLMs lies the transformer architecture. Transformers use attention mechanisms to understand the relationships between words in a sequence. For example, in the sentence, I hit the ball with a bat. The word bat depends on the context. So whether it's a baseball bat or a flying mammal, those are the things we need to consider here. Transformers excel at capturing such nuances, such as these. Transformers come in 3 flavors. Encoder-only models are great for tasks like sentiment analysis or classification. Decoder-only models, like GPT, are designed for generating text by predicting the next word. Encoder-decoder models combine both strengths and are often used for tasks like translation. Each architecture has trade-offs, so your choice depends on your specific use case. Beyond architecture, you will make several design choices. Residual connections allow data to bypass hidden layers, improving training efficiency. Layer normalization stabilizes training by rescaling values. Activation functions such as JLU or ReLU introduce non-linearities that let the model learn complex relationships. And positional embeddings encode token positions, helping the model understand these sequences. Now, how big should your models be? If it's too small, it underperforms. Too large, it risks overfitting. A good rule of thumb is 20 tokens per parameter. For example, a 10 billion parameter model might need 200 billion tokens to train effectively. Balancing size, compute, and data is critical. Training an LLM is no small feat. Mixed precision training, 3D parallelism, and zero optimizers are game changers. For instance, pipeline parallelism distributes layers across GPUs, while data parallelism splits training data. Together, these techniques minimize memory use and speed up training. Training isn't just about brute force, it's about stability. Checkpointing saves progress, allowing you to recover from failures without starting over. Weight decay regularizes parameters to prevent overfitting, while gradient clipping avoids exploding gradients that could disrupt training. These techniques ensure a smoother training process, even for massive models. Hyperparameters can make or break your training process. Batch size should balance memory use and training speed. Learning rates often follow a warm-up phase, increasing linearly before decaying. Dropout typically sets between 0.2 and 0.5, preventing overfitting by randomly deactivating neurons during training. Once trained, it's time to evaluate. Benchmark datasets like ARC and MMLU test the model's reasoning and knowledge. For example, a multiple choice question might ask, which technology was invented most recently? With answers like cell phones or airplanes. The model's ability to predict correctly reflects its understanding. While more nuanced tasks like truthful QA, human evaluation might be needed. Alternatively, metrics like BLUE or ROGUE provide automated assessments. Fine-tuned models such as GPT Judge can also evaluate outputs, reducing manual workload while ensuring quality. LLMs are incredibly versatile. From powering chatbots to analyzing specific papers, their potential is vast. Here at Neuralix, we apply AI to energy and manufacturing, solving real-world challenges with precision and efficiency. These aren't just abstract ideas, they are transforming industries. Thank you for taking the time to watch this video about building an LLM from scratch. Goodbye.